Right, in the last video we looked at the Gram-Schmidt process, and in this video we're going to build on that, showing an application of Gram-Schmidt to something called the QR decomposition, which can be used, for example, to help us solve linear systems. So let's say we have something like an n by n matrix A multiplied by a vector x is equal to b vector b, and we want to solve for x. So we know that x is going to be equal to a to the minus 1 b. The QR decomposition gives us a way of solving for x without actually having to compute a to the minus 1, though of course a to the minus 1 must exist. So the QR decomposition gives us a way for doing this, and the Gram-Schmidt process from the previous video is very much at the heart of it all. So we very much build on the previous video here. So what I'm going to do is we say that A is a square matrix. So let's say it's an n by n real matrix, and I'm going to write down its columns separately. So I'm going to say that A is equal to these column vectors that sit next to each other, A1, A2, up to AN. So these are just columns stacked next to each other. And then we know, like I say from the previous video, that we can use the Gram-Schmidt process to create from these vectors that are the columns of A. We're going to create this new set of orthogonal vectors, Q1 all the way up to Qn, that have the same span as these vectors here. So like I say, if you're not sure what that means, then that's all in the previous video. And we do that by, first of all, we set that Q1 is equal to A1. We then set Q2 equal to A2, but then minus the projection onto Q1 of A2. Then we carry on and we say that Q3 is equal to A3 minus the projection onto Q2 of A3 minus the projection onto Q1 of A3, and we keep going until we've got our set of orthogonal vectors. And then often what we do at the end is we normalize all of our Q's so that they have unit length. So in other words, we normalize them afterwards so that Qi transposed Qi is always equal to 1 for all of our Q's from Q1 to Qn, in which case they become orthonormal rather than just orthogonal. Okay, so we've used our Gram-Schmidt process to create all these orthonormal vectors that have the same span as the columns of the matrix A. So if we look at this first term here, bearing in mind that we may have that we've normalized Q1 afterwards, what we can say is that A1 is equal to some kind of constant times Q1. The two vectors point in the same direction, but potentially with different magnitude. So I'm going to write that down here. I'm going to say that A1 is equal to, so some constant. I'm going to write that as an R with a 1, 1 for reasons that become clear later. But the point is, it's equal to some constant multiplied by Q1. If we move on to the second term, so if we rearrange this equation in terms of A2, what we've got is the vector Q2, and then it'll be added to some kind of a projection onto Q1. Okay, so that means that A2 can be expressed as a constant times Q1 plus a constant times Q2. like I say, we have a Q2 and then a projection onto Q1 in that equation. So that means that A2 is equal to some kind of constant, which is going to be an R12, multiplied by Q1 plus another constant, which I'll write as an R22 multiplied by the vector Q2. I'm going to carry on in a similar way. We know that A3 is going to be equal to, so there's the vector Q3, and then we have a projection onto Q1 and a projection onto Q2 as well. So really continuing, following the same principle, we know that A3 is going to be an R13, some other constant, times Q1 plus another constant, an R23, times Q2 plus another constant, which I'll write as an R33 times Q3, and so on. So what are these constants, the R's? Well, we just have to remember that the Q's are orthonormal. We're going to start off with this first equation. If we pre-multiply by Q1 transposed, then Q1 transpose Q1 is just equal to 1. And so what we end up finding is that the constant R1 is just going to be equal to Q1 transposed multiplied by A1. So again, that's because of this orthonormal property. If we look at the second equation, similar process. What we're going to do is, first of all, pre-multiply by Q1 transposed. So this Q1 transposed times Q1 just goes to 1. And then Q1 transposed Q2 will be equal to 0 again, all because these Q's are orthonormal by definition. So after all of that, what we find is that the constant R12 is going to be equal to Q1 transposed times A2. Okay, we have one more constant to find on this line. So same thing, we're going to pre-multiply now by Q2 transposed. Q2 transpose Q1 is equal to 0 by definition. Q2 transpose Q2 is equal to 1. And so we end up finding that R22 is equal to Q2 transposed A2. Then we can keep repeating that process on, and what we find is that in general the constant Rij is equal to Qi transposed multiplied by Aj, or in other words, it's equal to the dot product between our ith orthonormal vector that we found from the Gram-Schmidt process and the jth column of our matrix A. So now we're going to assemble these results into basically a sort of matrix form, and in doing so complete the QR decomposition. So again, we're going to write our matrix A as columns. So on the left hand side I'm going to say I have a matrix that's made up of columns of A1, A2, A3 and so on, and it's going to be equal to, so first of all I'm going to create a new matrix from our Q's, from our orthonormal vectors. So I'm going to create a matrix that is made of, the first column is Q1, the second column is Q2, the third column is Q3, and so on. And then I'm going to have some other matrix here on the right hand side, which we'll have to define. Okay, well first of all, we know that A1 is equal to Q1 just multiplied by a constant R1. So in the top left hand corner of this matrix I can just write R11, sorry. And then again, this is just standard matrix vector multiplication. You have a Q1 times R11 plus, but there's no projection of A1 onto any of these other vectors. So the rest of this matrix can just be equal to zeros. The rest of this column, rather, all the way down to the bottom. A2, the column A2 is going to be equal to a Q1 times R12 plus a Q2 times R22. But there's no other component projected onto the other Qs. And so again, the rest of this column can be equal to 0. So I'm sure you can kind of see the pattern here. This column A3 is going to be equal to, well, Q1 multiplied by R13. Again, looking up here, plus Q2 multiplied by R23 plus Q3 multiplied by R33. And then everything else in that column is equal to zeros. And we keep going like that. Generally speaking, and in the end, what we end up with is an n by n matrix where the final column is given by R1n, R2n, all the way down to Rnn, where, as we know from up here, each of these elements of R is given by, so Rij is equal to Qi transposed Aj. So now we have this matrix here, which we say is upper triangular. So it's upper triangular because it has this diagonal. Everything above the diagonal has values and everything below it is equal to 0. So that's called an upper triangular matrix. So putting all of this together, we know that this is the matrix A. This thing, a matrix that we created out of the orthonormal vectors Q. So we're going to call that a capital Q. And this thing is, as you might have guessed, we're going to call R, this upper triangular matrix. So finally, what we have is that A is equal to Q multiplied by R, where the elements of R are defined by saying that Rij is equal to Qi transposed Aj for the case where I is less than or equal to j. So this is saying that this is defining the upper triangular part of the matrix, and it's equal to 0 otherwise. And that completes our QR decomposition, where the columns of Q have come from applying the Gram-Schmidt process to the columns of A. Okay, so that's our QR decomposition. And now, again, to kind of give it a bit of context, we'll show one of the things that you can do with the QR decomposition, that is how it can help you solve a linear system. So we have, what we want to do is we have Ax is equal to B, where we want to solve for x. We're going to take the QR decomposition of A. So what we have then is that QR x is equal to the vector B. We're then going to pre-multiply by the matrix Q transposed. So Q transpose Q, Rx is equal to Q transpose B. Q, the columns of Q are orthonormal by definition. So that means that Q transposed Q is just equal to the identity matrix. So we end up with R times X is equal to Q transposed B. And then on the right hand side here, what we have is an n by n matrix multiplied by an n by 1, i.e. column vector. So that's just going to be some other n by 1 vector. So I'm just going to write that as y, just to keep the notation simple. So what we end up with is R times X is equal to Y, where we want to find X. R is known and is upper triangular, and Y is known as well because we know Q and we know B. So fortunately, because R is upper triangular, we can actually now solve for X relatively easily using something called backward substitution, which for this video we'll just illustrate for the 3 by 3 case. So for the 3 by 3 case, what we have is that R is going to be equal to, so again it's upper triangular, so R11, R12, R13, and R22, R23, R33, with everything else set equal to 0. X has 3 elements, so x1, x2, and x3, and it's going to be equal to a y, which is a y1, y2, y3. With backward substitution, what we're going to do is start off solving for x3, then we move backwards to solve for x2, and then for x1. So to solve for x3, what we're going to do is look at what happens if we multiply this third row by this column, because we'll have a 0 times x1 plus 0 times x2 plus finally r33 multiplied by x3 is all equal to y3. And so that means that we can easily solve for x3 because we know it's equal to y3 divided by r33. So we've now solved the first element of our vector x. Now to get the second one, we're going to look at this second row of r multiplied by this column. So we have 0 times x1 plus an r22 times x2 plus r23 times x3 is equal to, and on the right hand side, y2. So if we rearrange this and solve for x2, you can see that x2 is going to be equal to, and we're going to have a y2 minus r23 x3, and then all divided by r22. Okay, and because we found x3 in the previous iteration, then we know everything here, and so we can solve for x2. So now we've solved for x3 and x2. Okay, so hopefully the pattern's obvious now, but we'll just do the final one just to be clear. So we're going to multiply this first row of r by this column. So that's an r11 x1 plus r12 x2 plus r13 x3 is now going to be equal to y1. So again, we're just going to rearrange this in terms of x1. So we know that x1 is going to be equal to, well, on this right hand side, we're going to have a y1 then minus all these other terms, so minus an R1, 2, x2, minus an R1, 3, x3, and because of this term here, it's all going to be divided by R1, 1. And again, we know all of the R's, we know y1, and we found x2 and x3 in the previous iterations. So now we've found x1, x2, x3, therefore we've managed to find x, i.e. solve this linear system without actually computing the inverse of A. Rather, instead, we've used the QR decomposition of A and then exploited the fact that Q is orthonormal. Okay, so that's basically the end of this video. So it's the QR decomposition, and it's really just showing what you can do with the Gram-Schmidt process, which we covered in the previous video. Showing how you can realize this decomposition, and then even further than that, you can use your QR decomposition to solve these linear systems without finding the inverse of A.